Here we go. Ladies and gentlemen, class recording has started. So, our plan for today looks like this. Over the next couple days, as we just saw in the calendar, there are a lot of problems that go along with this section. And we'll see that these problems all follow a very similar format because there's a reason why, and we'll talk about that reason here in just a little bit. But we'll start off today introducing them in what I think are probably the most simple kind of problems that we'll do. And then we'll gradually increase degree of difficulty as we go along the week, but hopefully showing you that these problems all fit a pattern. And if we can decipher the pattern, solving that problem becomes easier. Yeah? So the first thing I want to do for today is let's take a look on this sheet that is titled, not what I want to do, Calculating Centripetal Force, Friction as Centripetal Force. Last week, we introduced the idea of circular motion. And we talked about that circular motion is not a natural kind of thing. Why is circular motion not a natural kind of thing? Because of inertia, right? Inertia says go straight. Inertia doesn't say go in a circle. Meaning that something that's going in a circle has to have what? Net force. Net force causing an acceleration, and we call that acceleration what? Centripetal with a P. Okay? That being the case, like we just kind of working backwards, right? If it has acceleration, it has net force. That's going to be the key to solving these problems this week. The fact that an object that is moving in a circular path is accelerating. That acceleration is caused by a net force. If we can determine the net force, that's going to go a long way to helping us solve something about the motion of that object. So with that being said, let's take a look on this problem set that I gave you today at question number 1. So question number 1 says, a car with a mass of 1,234 kilograms approaches a flat curve on dry pavement that has a radius of 45 meters. What is the maximum tangential speed that the car could travel around the curve without sliding if the coefficient of static friction is 1.20? So this problem starts the way that all the other problems start. So instead of making you guys go through this exercise out loud, why don't we just go through the procedure here, right? So first things first. Right? Next. Good with those 4 things? Questions? Okay. Now, let's get down to solving this problem. Because this deals with forces and deals with an object accelerating, a free body diagram is going to be appropriate for us to draw here. So, I'm going to start off and I'm going to draw myself a ground. Now, the free body diagram for this problem is sometimes confusing to people. Okay? So first let me draw, then I'll explain. Okay? So here is a car that is coming towards you. Does that make sense? Your front view of the car. Okay. All right. So this car, hold on. I'm gonna move. Ooh, not what I wanted to do. Good Lord. There we go. Okay. Let's slide this over here a little bit. Okay. This car is undergoing acceleration. There are multiple forces that are acting on it. Let's draw some forces. What's the first one we could probably put in? Gravity, right? This car has gravity acting on it. Gravity acts straight down on it. That doesn't change whether it's going around a curve or not, okay? And at this point, I hope we're good about calculating the force of gravity, right? So we know that in order to calculate the force of gravity, we got to multiply m times g, okay? You know the mass of this object, so you should be able to figure out what the force of gravity acting on it is, and it's what? So what do we get when we get the force of gravity here? Anybody running through yet? What is it? 12,105 newtons. Okay. Now, before we draw any other forces, let's interpret the picture a little bit, okay? This car is coming out of the board and traveling towards you, but, like it says in the problem, it is not going straight. It says it's going around a curve. This curve comes out of the board, and let's say it's turning to your right, this car's left. Does that make sense? So it's coming out of the board and going this way. Okay? That being said, that orange dot would represent what? Not exactly the radius, but another important part that's kind of, it's what? It's the center of the circle. Okay? That's important because we know that if an object is traveling in a circular path, what has to be true? How does that happen? Is it accelerating? Yes. That means it has to have what acting on it? A force, but more importantly, a net force. And we call that net force, in this case, what? The centripetal force, right? What have we learned about centripetal force so far over the first week of doing this unit? It always points towards the center. So, there has to be a force that's acting like this. And we call that force the centripetal force. Okay? One more thing. If this car is coming out of the board and going around a curve to its left, your right, is it moving up or down? No, meaning there has to also be what? There has to be a normal force in this problem. How big is that normal force going to have to be? Same as gravity, right? So we'll draw it here like this, and then we'll take it up here, and then we know that F of n has to also be equal to 12,105 newtons. Okay? Good there? Okay. Now here's where this problem gets a little bit tricky. Okay? At least the first time we do it. We've already established that there has to be centripetal force pointing the way that it's pointing in this picture, because an object going around a curve has to have a force that points towards the center of rotation. That's that purple arrow. But we also said that centripetal force is not some new kind of force. Something has to provide centripetal force. For example, in the lab that we just completed, what kept the stopper from going in a straight line? The string, right? So the string, or the tension, provides centripetal force in that problem. In this problem here, what's keeping this car from going in a straight line out of the board towards you and making it go in the curve? Friction, right? Other than the fact that it gave us friction in the problem, that's what keeps your car from going in a straight line, right? We talked about in the wintertime, when it's icy, sometimes you don't have that friction. And what happens? You don't go in a curve, you go in a straight line, all right? But, that being the case, this purple arrow that we have labeled as F of C is also the force of static friction. There aren't two arrows there. It's the same arrow. That arrow represents static friction. It just so happens that that static friction is acting towards the center of rotation, and that makes it the centripetal force. Does that make sense? Don't confuse it in the fact that there's two arrows. It's one arrow. It's one force. It's actually friction, but because it points towards the middle, that makes it centripetal force. And that's how all problems in this unit are going to start. F of C equals something. Because centripetal force has to come from somewhere. In this case, we've established that F of C comes from where? What provides the centripetal force? The static friction. Does that make sense? This is how the problem is going to start. And this is how all problems in this unit are going to start. F of C equals something. Okay? At this point, we can start plugging in some things we know. Do we know how much static friction there actually is in this problem? Not yet, but we can figure it out, right? If we know the coefficient, 1.20 equals the force of static friction over the normal force, which we've already established is 12,105, so we can figure out what the force of static friction is. When you do that, you get 14,526. Is that good? Now, going back to our equation, we can plug 14,526 over here on the right-hand side. How much centripetal force do we need? Well, that depends on a couple of things. What does the amount of centripetal force required depend on? What factors influence the centripetal force required for an object to go in a circle? Mass is one of those ones, right? What else? The tangential speed, and then also the radius of the circle. Okay? Those three things influence how much centripetal force we actually need to make this turn. Do we have information that we need now? Well, do we know the mass? Yeah, that was given to us in the problem. Do we know the tangential speed? No, but that's what we're trying to find. And do we know the radius? We do. So we've got things that we need to solve that equation for one variable, which you can do now. Answer up on the board? Any problems? Good there. Alright. Questions? Okay. Why don't we do one more example? We'll change a couple of things up in this example, but I think you'll see that this problem very similar to the previous problem that we did. So let's take a look at question number 3A. Question number 3A. Question number 3A says, a 50-gram mass is placed on a rotating platform at a distance of 0.120 meters from the center. The turntable is switched on and it eventually rotates at a rate of 33.3 RPM, revolutions per minute. Part A says, what is the coefficient of friction between the mass and the platform? So, as we've just discussed, right? That's my unknown, okay? But that coefficient of friction depends on two things, right? In order to figure out the coefficient of friction, we need to know the force of static friction and we need to know our normal force. Okay? We We need to know those two things in order to figure out our coefficient. Okay, going through the problem. Told us that the mass was 50 grams, but we don't want our mass in grams, we want it in kilograms. So we'll change it just like that. Distance of 0.120 meters from the center means our radius is 0.120. And here's where this problem starts to get a little tricky. Rotates at a rate of 33.3 RPM, revolutions per minute. That's going to be our what? That's going to be our velocity, but is that the unit that we want velocity in? Okay. Well, 60 is going to be one of the things we have to do. Okay. So we got that this is 33.3. Now, write it this way. It's 33.3 revolutions over 1 minute, right? So what's multiplying by 60 going to do for us? Turns minutes into seconds, right? So if we do it with a conversion factor, 1 minute over 60 seconds, right? And that'll give us revolutions per second, but we don't want revolutions per second. What do we want? Meters per second. Do you know what we're going to do with that?
Times the radius.
Okay, not the radius. Okay, here, if we're setting up another conversion factor, revolutions has to go on the bottom, and meters has to go on the top, right? What does the circumference give us?
The full distance around 1.
How many revolutions?
1.
So 1 revolution would be equal to 2 pi r meters. Does that make sense? How we're turning this revolutions per minute into meters per second. Okay. And then this, we know r, so we can figure out what the circumference is. Anybody do that yet? Is it 0.754? Is that what it is? Okay. So 0.754 meters. And then when you multiply all that out, you end up with, I forget, what is it?
0.418.
Is it 0.41 or 0.42?
Well, if you round it, it's 0.42.
Okay, let's go with 0.42. Okay. Good there? Good for starters? Okay. I'm going to draw the picture a little bit different for this problem because you'll see it in multiple ways. You'll see it sometimes like this, where you're looking at it from the front, but sometimes you'll see the picture where you're looking at it from the top. So, here is my rotating platform, and here is my mass. And that mass is going in a circle like this. Does that make sense? Are we okay with that picture? So now I'm looking at it from the top instead of looking at it from the front. There's my center of rotation. Is this object accelerating? Yes. It has to have an unbalanced force. What do we call that unbalanced force? Net force. In this case specifically, because of the type of acceleration it has, it would have to be a, well, what path is it going in? It's going in a circular path, meaning that it has to have what? Centripetal force. What do you know about centripetal force? How does centripetal force point? Centripetal force always points towards the middle. So there has to be a force that looks like this, and we call it F sub c. Okay. Except we just established, what do we know about centripetal force? Does it stand by itself? It's got to come from somewhere. What's keeping this mass from just sliding off the edge of the turntable here? Friction. So just like our last problem, the centripetal force is coming from friction. Friction provides the centripetal force. Okay? This is not two separate arrows. It's the same arrow. These two things are the same in this problem, and that's how we start this problem. F of C equals static friction. Every problem in this unit starts off with F of C equals something. Okay? Do we know how much static friction we have in this problem? Well, you can figure it out. You can't figure it out from the coefficient though, because we don't know that. But we know that that static friction has to be doing what? It's providing what in this problem? Centripetal force. Do we know how much centripetal force there has to be? We can figure that out, right? M d squared over r, and all together, those are going to give you the static friction force. Now you can plug those things in and figure out what it's going to be, okay? Here's the one thing that some of you probably see, but some of you might not, right? In order for us to find the coefficient of friction, we have to do two things. We just figured out a way to figure out the static friction force, but we also have to know what? Normal force, okay? In this picture, is there gravity acting on that mass? It's not showing up in this picture, but is gravity still acting on this mass?
Yes.
Sure. The way we're looking at it, which way is gravity acting in this problem? Like straight into the board, okay? But the acceleration is happening on the board. So if there's a force straight into the board, what else does there have to be? Force straight out of the board. How big? Same thing. So if I know gravity in this case, right, which I can figure out, I'll also know the normal force. Now I got the two things that I need. Does that make sense? And when you do that, if I remember correctly, this turns out to be 0.4905. This turns out to be 0.07 or something like that. Anybody run that through yet? Find out what this is. 0.07? 0.07 what?
3.7.
What is it?
3.5.
3.5? And then in doing that, this turns out to be like 0.12? 0.5. 0.15. Okay. All right. Good start today, everybody. Tomorrow, we will review the friction parts, and then we will get into the banked turn, talk a little bit about car racing, we'll watch a video, it'll be good stuff. Cars. Not the actual movie Cars. I could find it. Yeah, the dirt track, yep. Actually, that's not bad. I'm gonna have to look that up actually tonight.